This video is about the Materials Details page, which contains all the materials data for individual materials. So let me start by finding a material. So I will pick strontium titanate. Alright, so I have my results, and to get the details page, I click one of them. So let me click the first one, and here is the details page. So over at the top left, I have the formula, and I have the materials ID. And this materials project ID uniquely identifies this entry versus other polymorphs of this compound. One note about the chemical formula: if you're used to perovskite type compounds being labeled A, B, X3, where A is 12-fold coordinated and B is 6-fold coordinated, Materials Project won't always list the elements in the order that you or a chemist would expect. So don't put too much meaning in the element order that you see in these formulas. Now, there are a lot of properties here that you can get in the details page, and it can be difficult to know what all of them are. So one thing that we've added are these help guides. So if I click the help guides, what it shows me is a brief description of all of these different properties that we've computed. And in many cases, it actually gives links and a description of how accurate we expect these properties to be. For example, for the band gap, it says they're severely underestimated, typically about 50%. And then there's these links that actually bring you to more documentation. So here's the calculations guide, and again, there's links like accuracy of band structures, which give you more information about what to expect. So if you're just starting out with a details page, the help guides are a useful tool to get yourself oriented. For now, I'll hide them. The next thing to notice are the crystal structures. So here towards the left, we have an interactive crystal structure for strontium titanate. So if I click and drag, it actually rotates the structure so I can see a 3D view. There's also other options, for example, to turn on and off the polyhedra or to do space filling mode. And then over here there's instructions for doing more things like zooming in and out, or also rotating across the different axes, which is Option click in Mac and Alt click on the PC. Now on the right is actually the detailed lattice parameters and the angles that we get for this structure from the computation, along with the optimized atom positions. Now one question that we get for symmetric structures like this tetragonal perovskite is why the lattice parameters and angles aren't what you would expect. For example, for tetragonal structures, people usually expect 90-degree angles for all the different alpha, beta, gamma, but here you see that two of the angles are about 120 degrees. The reason for the discrepancy is because there's lots of different cell settings in which you can represent a crystal structure, and by default we compute things in the primitive cell settings, and that's what we actually display here. So all these coordinates and these lattice parameters are for the primitive cell setting. Whereas over here we're actually showing the crystal structure in the conventional standard setting, which is more what people expect. You can get the positions for any setting by switching between these different modes and downloading the CIF file, which contains the coordinates and the angles. There's also options to download the file in other file formats, for example in POSCAR format, or to also get VASP input files for computing the structure yourself. Finally, there are these tags that we've parsed from the ICSD database that are used to identify and notate this structure, and these tags are searchable in the material search interface. Now, in addition to crystal structure, we've computed many different properties of the material, and again the help guide has more details about what these are, including the crystal symmetry. Scrolling down a little bit further, we see the electronic properties of the material in an interactive band structure and density of states plot. For example, if you hover over the points, you can actually see energy values, and actually if you click and drag, you can zoom in on this plot and interact a bit more. Towards the right with the density of states, here we see the total density of states, but you can also project on atoms and on orbitals. So if I click Atom Projected, I can actually see that the conduction bands are these purple atoms, which are titanium, and then the valence band is mainly blue, which are oxygen atoms. So I can kind of see the character of the conduction and the valence bands. You can also project on orbitals. So for example, the conduction band are mainly these titanium d states, and then the valence band are mainly these oxygen 2p states. Scrolling down further, we see the calculated Xrd pattern. So these Xrd patterns, remember, we tend to underestimate lattice parameters in the GGA computational functional, and so that affects the d-spacings that you get when you actually see these calculated patterns. And there is a reminder here with this warning: calculated Xrd tends to underestimate the lattice parameters. By default, the diffraction patterns are for copper K-alpha radiation. You can actually see the patterns for different wavelengths by clicking these buttons. So this is silver, molybdenum, etc. Now, you can download the XRDs using this XRD JSON button. Often theorists that visit the materials project want to know the details of the calculations so that they can better evaluate the data. Over here, we show some of the basic parameters used in computing these compounds. So for example, the functional is here, GGA, as well as the pseudopotentials, so VAS-PAW pseudopotentials, with the tag of the type of pseudopotential that's used, which determines the number of valence electrons. You also list the energy cutoff, the U values in case GGA plus U was used, as well as the total number of irreducible K points used in the structure relaxation run. This is the total energy computed by VASP. And finally, for some of the apps, we actually correct the energy in order to get more accurate results with respect to experiment, and the corrected energy that we use in materials project is listed here. You can get more details by clicking this "How do we arrive at this value" button, which lists all the different corrections and where they came from. Now, if you're a theorist, you know that all this data comes from more than one calculation, and each of these calculations have slightly different calculation parameters. So if you click this More Details button, it actually brings you to all the different calculations that were used to construct this details page. For example, this was the band structure calculation where the K points were done in align mode. This is the optimized structure calculation where we actually relax the cell coordinates. And this is, for example, a uniform dense K point mesh that we use for certain properties as well. For all these calculations, if you scroll down, you actually see the INCAR, which is a VAS-specific input file, and all the tags that we used when computing this compound. You can also see the POTCAR tags used, as well as the K points that were used. And you can see the direct and derived outputs from each of these calculations. So if you're a theorist, there's lots more information to dig into for these materials project details pages. Next is a section that's in beta right now, which is user data contributions, where people that have their own data on these materials can contribute that data to materials project. For example, the Technical University of Denmark has actually contributed higher quality band gap data that they've computed with a functional called GLLB-SC. For example, this functional gives a computed band gap value of 3.07 eV, which is closer to experiment than the 1.85 eV that we get using the typical GGA functional. This user data section might move or change as we experiment more with data contributions. Finally, Materials Project keeps track of the provenance and history of every crystal structure that's listed on the site. For example, we list the ICSD IDs that match this crystal structure. There are multiple duplicates in the ICSD ID, all with the same crystal structure, and that's why you see multiple codes listed here. This JSON history has a comprehensive record of what was done to this crystal structure. For example, we started specifically with ICSD entry number 170091. We used the code called CCTBX in this case in order to convert this structure to explicit atom positions. And the details of the parameters used are here. And then finally, Materials Project did a structure optimization using the GGA functional to end up with this MP4651 material. In addition to this detailed history, you can show citation information. So this crystal structure is based on work from Materials Project, and this is a citation from Materials Project for doing the structure optimization. But also it's based largely on the experimental work from this paper by Suda, 1995. And it was listed in the ICSD database as well. So in order to cite this specific crystal structure, these are the citations that you should be using.